Hello, welcome back to the NPTEL online certification course on deep learning. So for last few classes we are talking about the generative model, and a particular model that we are discussing is a variational autoencoder. So we have started our discussion on the variational inference, which is one of the theoretical modeling technique of the variational autoencoder. So what we have discussed in our previous class is that Z is a latent vector, and when this latent vector Z is fed as input to your decoder or the generator is expected to reconstruct your signal or the data X. Now, for X's of different categories, Z's will have different distributions. So, what I need to compute is a posterior probability, that is P of Z given X, which is nothing but P of X given Z into P of Z upon P of X, where P of X is integral of P of X given Z Pz dz. Now, here we have seen that the first problem that we faced is that this integral is intractable. So, because this integral is intractable, we cannot easily compute P of Z given X. So, P of Z given X also becomes intractable. And the reason we said that why this is intractable is Z is a multi-dimensional vector. The dimensionality of vector Z can be 10, it can be 15, it can be 100, it can be 500 and so on. And because it is a multi-dimensional vector, when I take this integral P x given Z P z dz, this integral also have to be taken, integration has to be performed over multiple dimensions, which is not an easy task. So, in order to solve this problem, we have mentioned that there are two different ways. One is you go for Monte Carlo solution simulation, and the other approach is a variational inference approach. So, the technique that we are discussing is what is known as variational inference approach. So, in this variational inferencing technique, what we have assumed that even though P of Z given X is intractable, but we assume there is a tractable distribution Q. This Q may be Gaussian, for example, and we want P of Z given X to be similar to Q of Z given X. So, if I want to do that, then basically what we have to do is I have to play with the parameters of Q, which are nothing but mean and standard deviation if it is a Gaussian distribution. So, we have to play with these parameters of this distribution Q, so that Q matches closely with the probability P of Z given X. Or effectively what we want to do is we want to minimize the KL divergence between P Z given X and Q Z given X. So, the KL divergence of P Z given X with respect to Q Z given X. So, our objective is to minimize KL divergence of P Z given X and Q Z given X. So, this is the objective with which we started. So, this is a minimization problem, minimization of the KL divergence of Q Z given X and P Z given X. Then through a series of derivations in the previous lecture, we have seen that the scale divergence of Q Z given X, P Z given X is equal to the sum of minus Q Z given X log of the joint probability P x given P x Z upon Q Z given X plus log of P x. I can rewrite this expression as log of P x is equal to KL divergence Q P plus sum of Q Z given X log of P x Z upon Q Z given X, where the summation is taken over Z. And then we have seen, so this is what we have derived after a series of derivations, starting from minimization of KL divergence Q P. Now, here we have seen that because X is your training data and which is given, so the left hand side, which is log of P of X, that becomes constant. And we started with our aim to minimize the KL divergence Q P between Q P. So, you find that this right hand side, because the left hand side is constant, log of p of x is constant. So, right hand side the KL divergence of q given p plus sum of q log p upon q, this is also constant. So, as this right hand side is constant and we want to minimize the KL divergence. So, if I want to minimize the KL divergence, that becomes equivalent to maximizing sum of qz given x log of pxz upon qz given x when you take the summation over z. So, this minimization of KL divergence between q and p is identical, becomes same as maximizing this quantity sum of qz given x log of pxz upon qz given x. And this is the term which is known as variational lower bound. Now, why this variational lower bound, or what is this variational lower bound? You find that as we have just derived, that log of p of x is equal to KL divergence QP plus sum of q log of p upon q summation over z. And we know that KL divergence is always greater than or equal to 0. So, we have seen before that KL divergence is not symmetric. So, if I want to find out KL divergence QP and KL divergence PQ, they will not be same in general. But the KL divergence is always greater than or equal to 0, and it will be equal to 0 when Q equal to P, obviously, because log of P by Q is when P and Q is same, then log of P by Q is log of 1, which is equal to 0. So, when P and Q are same, then KL divergence is 0, but if P and Q are different, then KL divergence will be greater than 0. So, KL divergence is always greater than 0. So, again analyzing this right hand side, you find that we have seen that our Px was intractable. And here you find in this expression, in this case, when I consider this particular expression, this is constant, this is always greater than 0, and if this KL divergence is equal to 0, then log of P of x is same as this particular term. Let me call this term as L. So, log of P of x will be equal to L, which is sum of q z given x into log of P x z upon q z given x. But if this is greater than 0, if this is positive, say some value epsilon, then your log of P of x will be epsilon plus L. That means L will be P minus epsilon. So, that clearly says that this L, which is sum of q z given x into log of P x z upon q z given x, this quantity is always less than or equal to log of P x, right. So, we know that P of x is intractable, as a result q log of P of x is also intractable, but I know what is its lower bound. And what I want is, I want to maximize this P of x, but which is intractable. So, I cannot directly do it, but I have a lower bound. So, because I have a lower bound, if I maximize this lower bound, and I know log of P of x is always greater than this lower bound, greater than or equal to this lower bound. So, if I maximize the lower bound, then effectively I am maximizing log of P of x or maximizing P of x. So, that is how this concept of lower bound comes. So, effectively the problem has boiled down that we started with our aim to minimize the KL divergence PQ, and which has boiled down to maximization of the lower bound, where lower bound is q z given x log of p x z upon q z given x. So, this minimization problem has been converted to the maximization of this variational lower bound term. So, our aim is now that we want to maximize this variational lower bound, which is sum of q of z given x into log of p x z upon q of z given x, which will be same as log of q z given x q z given x into log of p x z into p z upon q z given x summation over z. They are equivalent because pxz, the joint probability, is nothing but px given z into pz, right. So, I can always write that variational lower bound L is equal to qz given x log of px given z into pz upon qz given x, take the summation over z. And this is the term that we want to maximize. So, effectively we want to maximize this. Again, let us see that this term, that sum of qz given x into log of px given z into pz upon qz given x, this can be written as sum of qz given x into log of px given z plus summation of qz given x into log of pz upon qz given x. And if you look at this second term over here, you find that second term is again another KL divergence, right. So, what we have is, if you further simplify this, you find that the first component of this expression is an expectation of log of px given z, where the expectation is with respect to qz given x, and the right hand side is negative of the KL divergence between p q z given x upon p of z, and this entire expression I want to maximize, right. So, if I want to maximize this entire expression, that means effectively what I have to do is I have to maximize p of x given z, and I have to minimize the KL divergence q of z given x p z, right. So, now let us see that how this maximization problem can be translated to an autoencoder architecture. So, here you find that I have few terms. One is qz given x, which tells you that given your training data x, the probability of your latent variable or the latent vector. Similarly, p of x given z tells you that given a latent vector z to the decoder or to the generator, the probability of generating the data x. So, that is p of x given z. And I have another term which is p of z, that is the probability distribution of the latent variable or the latent vector z itself. So, if I translate this maximization term in the form of an autoencoder, I will have something like this. So, this is what was our graphical model, that given z, you can generate x following p of x given z, that is the generator part, and given x, I can get the latent variable z following q of z given x, which is my encoder part. So, this is what is the graphical model, and the corresponding neural network can be done like this, that both p and q can be implemented using neural networks, and the neural network will be something like this, that q z given x now is modeled by the encoder network, and p of x given z is modeled by the decoder or the generator network, and in between I have z, which is the variable or the latent vector which is generated by q z given x. Now, if I simply go by this, you find that it becomes an autoencoder model. But what makes it variational autoencoder, not just autoencoder, is that along with z, I now have a distribution which is p of z, which was not there in traditional autoencoder. In variational autoencoder, I have this p of z term. So, the encoder in this case does not give me a deterministic latent vector z, but the encoder gives me a distribution of the latent vector z. And what we effectively do is, during generation or during decoding, that you sample a vector from this latent distribution of the latent variables, and that sample is fed to the decoder or the generator, and the generator generates the corresponding data, which is x, right. So, this is what is our neural network for realization of that maximization problem. So, this Z code that we get now, as we have just said, it has to match with the distribution Pz. And what we will do is, we will decide a prior for this Pz, that is prior distribution, which will be chosen for this distribution Pz. And usually, this Pz is chosen to be a normal distribution with 0 mean and unit variance, and we assume that the covariance matrix is a diagonal matrix. That means, it is assumed that the components of the latent vector, they are independent of each other. So, as a result, the off diagonal elements in the covariance matrix will be equal to 0, and because every component will have unit variance, so all the diagonal elements will be equal to 1, or in other words, your covariance matrix is an unit matrix. So, this normal distribution that is assumed for Pz is n of 0 I, and this is the prior that will impose on Pz. So, what finally our variational autoencoder gives is that instead of generating a fixed code for an input to the decoder, the encoder now gives you a parameter of the distribution of the latent code. So, for a given input x, the encoder generates a mean vector mu x, and it generates a diagonal covariance matrix sigma x. And what we need is, we need to sample a vector z from this distribution, and that vector z, which is now my latent vector, has to be passed to the decoder or the generator, and the generator will generate the data accordingly. So, this is what is our variational autoencoder, and in explicit form, in the architecture of a neural network, it looks like this. So, here you feed in the data x to the input of the encoder. The encoder gives you the distribution of the latent variable z. So, it gives you the mean as well as the variance. Then you sample a z from this distribution and feed this z to your generator or the decoder network, and the decoder network gives you the reconstructed output x hat. Now, you find that when we talked about the traditional autoencoder, we said that the decoder in a traditional autoencoder was not of interest. In traditional autoencoder, our interest was the encoder part, because we wanted to encode the input data, or the input data has to be represented in a compressed form, which is useful for classification or for understanding. In case of variational autoencoder, our aim is exactly opposite. After your network is trained, we are no more interested in this encoder part, because the encoder has already given you the distribution parameters mu and sigma, and once I have this, I am only interested in the decoder or the generator part, because what I want is that, because this mean and variance or the parameters of the distribution of the latent variable is already known, I want to sample a latent vector z from that distribution. That sample is fed to the decoder, and the decoder has to give me the output x hat. So, this encoder part is not of interest. We are not interested in the encoder part of the variational autoencoder or in a generative model. But as we have seen in case of traditional autoencoder, where after training you simply discard the decoder. Similarly, in this case, after the training is over, or once you learn your distribution of the latent variables, you can discard the encoder part, because I don't need it anymore for the generation or the decoding purpose. So, that is what your autoencoder is. Now, again we have certain problems that you find that in this particular operation, we had an operation of sampling involved, because the encoder has given you the distribution parameters, and from that distribution have to sample a z to be fed to the decoder for generation of the data. Now, this sampling breaks the computational graph, and it hinders the gradient descent based optimization algorithm, because through a sampling operator I cannot pass the gradient. So, that is the problem. So how do you solve this problem? So effectively what we have is, if we put in the form of a graph, so this is what I have. This is the graph. What the encoder has given me is the mu and sigma. Those are the parameters of the distribution. And then what you do is, you sample a z from this distribution q z given x, for which I already know the parameters mu and sigma, and this sampled z is fed to the decoder for decoding or generation of the data x. And because I have a sampling process involved, my back propagation learning cannot work anymore, because through a sampling operator, the sampling operator does not support back propagation. So what you do is, you use a trick which is known as re-parameterization trick. So in this re-parameterization trick, what you do is, you dissociate the sampling operator, the sampling operation from the network. So what you do is, you sample from a normal distribution with zero mean and unit variance, and after you get a sample, you re-parameterize it. So suppose I sample a vector say epsilon, a variable epsilon, then I re-parameterize it in the form z is equal to mu plus sigma times epsilon, where mu and sigma are the parameters which are given by your encoder network. And once you do this, you find, as has been shown over here, this is my network part and this is the sampling operator. The sampling operator is now dissociated from the network. What we are doing is, we are sampling epsilon from a normal distribution with zero mean unit variance, and that sample epsilon is now converted to z, mapped to z through these parameters mu and sigma. And once it is done, now it is fed to your network. So this re-parameterized vector is now fed to the decoder or the generator, and the generator gives the output. Okay. So as this sampling process has been now kept out of the network, so as a result, I solve the problem, or I avoid the problem which we faced earlier, that the sampling process or the sampling operation does not support backpropagation. So now with this, I can easily go for backpropagation, as shown over here, that as I have the latent variable z, I can take the derivative of my final output with respect to z, or the error loss function with respect to z. Of course, there is a chain rule involved in it, because final loss function may not be directly visible to z. So as a result, to compute del L del z, where L is your loss function, I may have to apply chain rule, and then I can compute del z del mu. I can also compute del z del sigma, as has been shown over here. So now your backpropagation can simply follow this path as well as this path, where the sampling process does not take place, or the sampling process does not hinder the backpropagation operation. So because of this re-parameterization, it enables us the optimization of the parameters of the distribution following backpropagation, while it still maintains the ability to randomly sample data or sample a latent vector from that distribution, because we have kept the sampling process out. Right. So let us try to see that how this cost function can actually be coded. So you remember that the cost function that we wanted to maximize is q of z given log of p of x given z, expectation value of that, where the expectation value is with respect to q z given x. minus KL divergence of QZ given X PZ. And this is the loss function or the cost function that we wanted to maximize. And if I want to do that, what I have to do is I have to maximize the expectation value of log of Px given Z, and I have to minimize the KL divergence Qz given X Pz. So, I have a maximization operation involved, I have a minimization operation involved. So, if you look at this maximization part, that is maximization of the expectation value of log of P of x given Z with respect to Qz given X, this is a maximum likelihood estimation. And you find that my decoder is just a neural network. So, once I have a Z, my output x hat, that is deterministic. There is no non-determinism involved in it. So, this P of x given Z is equivalent to P of x given x hat, where x hat is your reconstructed value or the generated data. And this effectively means that this effectively tells you that you have to reduce your reconstruction error between input vector x or input data x and the generated or the reconstructed data x hat. And this is similar to what you do in case of a discriminative supervised model, for example, logistic regression, SVM or linear regression or all that. So, in other words, given an input Z and an output x, we want to maximize the conditional distribution P of x given Z under some model parameters, and we have to play with the model parameters, we have to modify the model parameters so that this distribution P of x given Z can be maximized, or P of x given x hat can be maximized, or the reconstruction error between x and x hat can be minimized. And this can be implemented using any classifier with input Z and output x, then optimize the objective function by using, for example, say log loss or regression loss. So, that is how the maximization part over this can be implemented. And for minimization of the KL divergence, what you do is you assume that Pz follows a normal distribution with 0 mean and unit variance, so that we can play around with the parameters of Qz given x towards this normal distribution, or the parameters of Qz given x can be pushed towards this normal distribution, and that is how the KL divergence has to be minimized. So, assuming this Pz, the distribution Pz to have a normal distribution, that has two advantages. Firstly, because it is a normal distribution with 0 mean and unit variance, I can easily sample a vector epsilon from this distribution, right? And then we are going for reparameterizing. And assuming this Qz given x to be Gaussian distribution with parameters mu x and sigma x, that allows our KL divergence between Qz x Pz to be in closed form, and that becomes easy for optimization. So, I will stop this lecture here. In our next lecture, we will discuss from this point, and we will also briefly talk about another generative model, which is known as generative adversarial network. Thank you.